Manual boosts break as soon as your queries change. I'll show you how to train an XGBoost LambdaMART ranker that combines BM25, embeddings, and click features into one search model. This is the pattern you'll be able to implement by the end, which learns from query document signals and ranks results while reporting ranking quality. I'm Professor Pi, teaching search and IR with simple Python. Search teams reach for LambdaMART when simple heuristics stop cutting it. You start with BM25 and a few boosts, and it works for common queries. But as queries drift or user behavior changes, those manual weights fail. LambdaMART gives you a way to learn the blend from data, not from guesswork, so relevance improves without constant hand-tuning. At a high level, LambdaMART learns to order documents for each query by optimizing a listwise metric. Imagine you have 3 signals per document: a BM25 score, an embedding similarity, and a past click count. The model learns how to weight and combine those signals to maximize a ranking metric like NDCG. We will build a small, transparent pipeline on toy data. It will show a manual blend baseline, compute NDCG to evaluate it, train an XGBoost ranker with query groups, add validation and early stopping, and finally re-rank a single query to see the difference. No heavy tooling, just readable data shapes and XGBoost rank training. This snippet assembles a small, readable query document dataset and scores it with a basic manual boost. It defines the arrays QIDS and docs to map documents to queries, and 3 feature arrays representing BM25, embedding similarity, and past clicks. The variable S computes a weighted linear score using simple coefficients that mimic hand-tuned boosting. A Boolean mask M selects documents for the first query, then argsort orders them by score. The code extracts the top document and its score to reveal how a manual blend ranks results. Increasing the BM25 weight will favor exact term matches more aggressively. The printed top document shows what the hand-tuned baseline currently prefers. Next, we measure how good that hand-tuned blend is. This example evaluates the manual blend by computing NDCG at 3 results per query. It defines relevance labels Y with a small scale from irrelevant to highly relevant. The function NDCG at K calculates normalized discounted cumulative gain by comparing the ordered relevance against an ideal ordering. For each query, the code selects its documents with the mask M, orders them by the baseline score S, and gathers the corresponding relevance labels. It appends NDCG at 3 for each query, then averages them to produce a single summary number. Raising K would reward deeper list quality. Lowering it focuses on early precision. The printed NDCG communicates how strong the manual boosting actually is. Now we swap the manual blend for a learned ranker using XGBoost. This code trains a LambdaMART style model with XGBoost's XGBRanker using an NDCG objective. It stacks the 3 features into X and computes per query group sizes in GRP, so XGBRanker knows where each query's documents start and end. The ranker is created with objectives set to rank NDCG, a tree depth of 3, and a modest learning rate. Then fit uses group to respect query boundaries. After training, predict returns model scores for all documents. The list comprehension assembles NDCG at 3 per query by sorting documents by pred and passing labels into NDCG at K. More trees can raise accuracy but risk overfitting. The printed NDCG shows the trained model's ranking quality on these examples. Next, we add validation and let the trainer pick the best iteration. This snippet adds NDCG-driven evaluation and early stopping with XGBoost's XGBRanker. It holds out query 3 as validation by creating a mask M and computes train and validation group sizes for rank-aware training. The ranker includes eval metric set to NDCG at 3 and uses early stopping rounds to pick the best iteration. The fit call passes eval set and eval group, so XGBoost reports validation NDCG per boosting round. After training, the code predicts on the validation slice and computes NDCG at 3 using NDCG at K to confirm the held-out performance. Increasing N estimators allows more capacity, but may overfit without early stopping. The printed NDCG and best iteration reveal a tuned point that the model selected. Now, we re-rank a single query to inspect the practical change. This example shows how to re-rank a query's results with the trained XGBoost model. It selects the documents for query 2 using mask M, then computes the original manual blend score, S0. The call to ranker.predict generates model scores for the same feature rows, representing LambdaMART's learned preferences. The code extracts the top document before and after, using argmax on S0 and the predictions, and reports whether the top item changed. If you increase training trees or add features, the re-ranked order may shift more. The printed before and after values make the re-ranking decision visible at a glance for one query. In real projects, this toy maps directly to a production flow. Replace the toy arrays with your BM25 outputs, a vector similarity column, and a click-through count. Train on recent query sessions with relevance labels derived from clicks or human judgments. Then serve model scores as a re-ranker after your initial retrieval stage. Recap. LambdaMART is a learned tree-based ranker that optimizes listwise metrics like NDCG. Use it when multiple signals need to be combined and manual weights start to fail. Caveat: it needs per query grouping and enough labeled examples, or it will overfit. Next step: tune the number of trees and early stopping based on validation NDCG, or swap the embedding similarity feature for another distance measure to see how it changes ranking. If practical IR and clear code help you, subscribe and watch the rest of the IR videos.